How's it going? So in this video here, we're going to be taking a look at the different types of channels that we have on our neuron, and we're going to be relating that to its membrane potential versus time. And so here on the y-axis, we have our membrane potential, which is going to be in millivolts, and here we have our time, which I'll draw on for you in a second. So if we take a look at our axon over here, or our neuron, we remember that in our input regions, we're always going to have our ligand-gated channels. And so our ligand-gated channel here is going to be in green, and what that's going to allow for is the influx of positive charge, or Na+. So Na+ is going to be coming into our input region. Now another type of channel that I forgot to mention in my last video was this black channel right here. And so this is going to be known as a K+ leak channel. And so what that's going to allow for is the leaving of potassium in our cell, from our cell. And so our leak channels are always going to be open. And so what is occurring in this input region is we're having this influx of Na+, but it has to counter this efflux of K+. And so depending on the amount of positive charge that we get overall from this leaving and this coming in is going to determine whether or not we generate an action potential. So let's say that we get enough positive charge into our input region. And if we look at this chart here, what that means is that we're slowly increasing our millivolt potential. We're slowly bringing in this positive charge. And one thing I forgot to mention was that inside of our cell, we're going to have a resting membrane potential of usually around -70 millivolts. And so that's going to mean our neuron is usually, the membrane potential inside of it is usually negative. And so by bringing in this positive charge, once we get enough positive charge, let's say we reach -55 millivolts. Well, once we reach that point, we're going to generate an action potential. So action potentials are important because they occur in an all or none fashion. If we reach this threshold of -55 millivolts for this neuron, then we're going to generate an action potential. But if we don't, let's say we reach -57 or -58, then we're not going to have any action potential at all. So let's say we bring in enough positive charge. This positive charge is going to build up, and once it gets to this Na+ channel over here, we remember that this is going to be our Na+ voltage-gated channel. And voltage-gated channels open in response to membrane potential or charge. And so once we bring this charge over here, that channel is going to open. It's going to allow for the influx of Na+ into our cell. And so what we have here is 100 millimoles of Na+ outside of our neuron and 10 millimoles of Na+ inside. And so what that's showing is that we have a lot more Na+ outside of our cell, or sodium. And so we're definitely going to be bringing in this Na+ down its concentration gradient once this channel opens. And so the bringing in of this sodium is going to generate is going to start our action potential, and this is going to be known as Na+ influx, or sodium influx. The sodium influx is going to occur bringing in our sodium into our neuron. And so by doing so, we're bringing in, or we're raising this membrane potential. So if you remember, it was around -55 millivolts in here, but by bringing in all this sodium, we're going to raise our membrane potential usually to around 35 to 40 millivolts. And at that point, our Na+ channel is going to inactivate. So no more Na+ is going to be able to come in. Well, once that closes, or once we reach that membrane potential, now our potassium voltage-gated channel is going to be able to open. And so if you remember, this one's also voltage-gated, so that's going to open in response to membrane potential. And so when that channel opens, what that's going to allow for is the efflux, or the leaving of potassium within our cell. And so potassium, K+, is going to be leaving. And so if you see here, we have 100 millimoles of K+ inside of our neuron, only 10 millimoles of K+ outside. So the potassium is going to be moving down its concentration gradient as well. So if we go back to this graph over here, by K plus leaving our cell, we're going to be decreasing our membrane potential. And so this is going to be known as K plus efflux, or the leaving of potassium. And so sometimes if our K plus efflux happens a little too much, it's going to result in hyperpolarization, where we're going to go past our resting membrane potential. And eventually, with different types of ATPases, we're going to be able to bring this back to our resting membrane potential of negative 70 millivolts. And so that is how one action potential occurs. There's going to be many of these occurring within our neuron. And so in terms of time here, these action potentials occur very quickly. And so for this one, we're looking at about maybe 1 millisecond. So 1 millisecond here to 2 milliseconds here. So very quick action potential.